So after engulfment, you have fusion of the lysosomes with the phagosomes. A release of digestive enzymes to break down the bacteria, so destruction or digestion. And finally, exocytosis. The vacuole fuses with the membrane, releasing the undigested material into the environment. Macrophages serve as scavengers and sentries. Pretty much they'll set up residency in tissues like we've talked about, and they'll engulf foreign material that they come in contact with. They'll engulf things that have been coated with complement. They'll engulf things that have been coated with antibodies. They can present antigens to T cells, and they can be activated by T cells. With macrophages, they can actually, if they need to, fuse together and form this wall around bacteria called a granuloma. So essentially the bacteria are walled off and prevented from spreading any further. We see those granulomas in people that have tuberculosis. The tubercles that develop in the lungs and elsewhere in the body are actually macrophages that have formed these thick walled structures around the bacteria to keep them from spreading. In addition to macrophages, neutrophils are also phagocytic. Now neutrophils, we mentioned that they are probably the most abundant white blood cell in the bloodstream. They're the first responders. When you have an infection and the messages are going out that you're being invaded by bacteria, neutrophils rush to the area and then they start devouring the bacteria. Neutrophils are big eaters, but they're short-lived. They only live a few days. Macrophages, much longer lived, probably don't eat as hearty as neutrophils would, but they're weeks, months in the tissue sometimes. Yes.
So the C5 and C3 are proteins that are part of the complement system that have been activated.
Yes.
Can you just go over one more time how that gets activated?
How the complement might get activated? A number of things could activate the complement, but one of them could be antibodies. So if there has been a recognition of a foreign particle and B cells releasing antibodies, those antibodies can then serve to activate complement, as though you get a cascade that way. Certain cytokines that are being released by cells can also serve to activate the complement. When we talk about activating it, really what you're doing is you're taking a protein that's got an active site that is kind of hidden. Okay, and all you do is you bind to that protein and it opens up that active site, and now it lets it carry out whatever reaction that it can carry out.
But it's not an enzyme.
It's not an enzyme, no. It's not catalyzing a reaction. It's a protein, yeah.
And C3 binds to, you said binds to, and then I lost it.
Well, it binds to bacteria. It can bind to molecules that are on the surface of the bacteria, and then that serves to flag it, if you will. So now that the macrophage recognizes the complement, it knows that this is something to engulf. Opsonicizing is a common practice with complement and antibodies. We'll see both of those, where they'll coat bacteria with complement, or they'll coat it with antibodies, and then that allows the macrophages to recognize those cells. Anything else?
But the macrophages can also recognize the toll-like receptors.
Yes. Yes, they can also recognize peptoglycan molecules, flagellin, sure, absolutely. So let's talk about inflammation. So we're talking about generally a coordinated response to an invasion, and there are 4 signs that we associate with inflammation: redness, swelling, heat, and pain. When you think about inflammation, the role of it is to limit the spread of the infection, limit the damage, and return the tissues to function, if you will. What can cause inflammation? Well, a number of things can do it. Tissue damage, damaged cells release cytokines, release chemicals that can serve to activate the system. Microbial products can cause inflammation. Again, this is where the toll-like receptors might come into play. If a macrophage has been activated because its toll-like receptors have been bound, it can release cytokines that could start the inflammation response. And finally, bacterial cell surfaces themselves. So with inflammation, what happens is you have damage done to the tissue. Okay, so now you've caused the tissues to release chemicals, cytokines, and what this does is a number of things, but the first thing is that the small vessels, the capillaries, dilate. They become larger. They allow for blood now, increased blood flow to the area. Right away then, this is where our redness comes from. Increased blood flow to the area. In addition to that, the cells that are lining the endothelial, or the endothelial cells lining the capillaries, start to spread out, if you will. The spaces between them get a little wider. And this allows fluid that is in the blood then to move into the tissues. So that you got fluid that starts to leak into the tissues. The increased blood flow causes the heat that you start to experience. But then the fluids that are seeping into the tissues, along with monocytes that are being grabbed and pulled in, neutrophils that are coming into the area as well, cause swelling to occur. So the swelling that you're experiencing is because of the fluid from your blood, from your circulatory system, moving into the tissues. And then this swelling, along with some of the chemicals that are being released, pyrogenes and others, the swelling can put pressure on the nerve endings. Chemicals themselves can cause pain, and so you have pain that develops from the inflammation. So at this point now, what you've got going on is that the cells that are there, the bacterial cells that are there, are being attacked by the neutrophils. They maybe are also producing products. They're multiplying as well. And so you've got kind of a battle going on at this site with your immune cells, macrophages, neutrophils mainly, and the bacterial cells. But in addition to being in this area where all this stuff is going on, these things are dendritic cells. We've introduced these already a little bit here. But these dendritic cells are also sampling the bacterial products. Okay, so they're taking samples as well. Now, eventually this fluid material is going to move into the lymphatic system. And so all of that bacterial product that we've been exposed to moves into the lymphatic system where we have our B cells and our T cells. That's where our B cells and T cells become exposed to these bacterial products and will actually trigger an acquired immune response to those cells. One more thing that we can say about infection here and non-specific responses. Fever. Our temperature, 37.8 generally. Give or take a few points, I suppose. Gets up to 100, 102. We're running a fever. Gets up to 104. We start to get concerned. That's kind of high. 106. That's way high. And we work to bring it down. But what's the point of a fever? If we think about the reason that we have a fever, it's because we have a bacterial infection. A bacterial infection means, we've got bacteria growing in our body and we want to limit the amount of growth that we have going on. We've talked about this with bacteria having very narrow ranges or very broad ranges, depending on the microbe that they can grow. But generally, they have an optimum temperature at which they grow best. Microbes that inhabit the body grow best at about 37 degrees. If you can raise that temperature up to, 39, 40, 41 degrees Celsius, I don't know how hot that is, but if you can get it up there, you may not kill the bacteria, but you can slow their growth so that it's not at the optimum rate. So that gives your immune cells a chance to fight them off. So fever works to slow the bacterial growth. Now, the reason we can't let it get too high is because if it gets too high, it'll start to denature our own proteins. And then our own proteins don't function. And then what good is that? So a minor fever is good. It reduces the bacterial growth that's going on from the infection. In addition to that, elevated temperatures can speed up enzyme activity. So it can help our immune response to the microbes as well. Yes?
But I thought enzymes work best also at body temperature, so if you raise the body temperature, it won't denature them?
Well, it will if you raise it too high, but it speeds up their activity. Small degree raises, 1 or 2 degrees, will speed up the activity of the enzymes. If you raise it up to 106 degrees, yeah, you will start to denature the enzymes, but a couple of degrees will speed up their activity. Okay, so that brings us to chapter 16, our discussion on the adaptive immune system. So what we're talking about now is an immune response that matures or develops throughout life. So as a baby, newly born, you really don't have much protection from the microbes. Protection that you do have is coming from your mother. She passed on some antibodies across the placental wall initially, so you had some protection there. And through mother's milk, she is giving you some antibodies as well. But that's going to be short-lived. In about 6 months, you're going to be out of those antibodies, and you're going to have to start to build your own immune system. And that only happens through exposure to antigens, to foreign material, to microbes. The adaptive immune response is specific. The cells and the molecules are binding to specific bacteria or specific cells. If it doesn't recognize the molecule that's on that bacterium, then that bacterium is not going to be bound by our immune system. And will then have free reign, if you will. And then our adaptive immune system has memory. And this is why it works, is because it has memory. It remembers the microbes that we've been exposed to. The reason you don't get the flu twice in the same season from the same virus is because of that memory. When we talk about the adaptive immune system, there are two responses. There's the primary response, and that's the initial exposure to the antigen. So the primary response, we'll see, sometimes can be quite delayed. Gives the microbes chances to grow, spread the infection. A secondary response, though, happens when you've been exposed to that microbe for a second time. It's a much quicker response and prevents the spread of the microbe, prevents the infection from becoming established. You have two strategies that are employed. Humoral and cellular. Humoral immunity refers to stuff that's happening in the circulatory system. So stuff that's happening in the bloodstream, working to eliminate antigens that are outside the cell. Cellular adaptive immunity then, working to eliminate antigens that are inside the cell. So infection has taken place.